Yes, questions?
It's kind of a mathematical question, actually, regarding the second question of the finite experience.
Okay.
May I ask Henry?
Sure.
I used the principle of superposition and symmetry together, actually. Contribution from the pass line on each quadrant will be the same. So I just tried to potentially do the first quadrant and multiply by 4 to find the potential, but integral is a bit tricky. I tried to partially switch the cylindrical in order to.
Now, the problem is if you switch to cylindrical, the shape of the plate is not cylindrical.
Yeah, I know that. I keep the limits as a Cartesian, so evaluated the integral, like infinite integral, but I don't plug the limits in.
Mm-hmm.
So
You cannot. Well, stick with the Cartesian. What kind of an integral did you obtain?
dA over
dA over?
in square root x squared plus y squared plus b squared.
Now, my question is, what is dA, what is x, what is y, how are they related? dA is dx dy?
Yes.
Okay. And, okay, so let me write it in this form. dx, so you are limiting yourself to... You are limiting yourself to one of the quadrants, which, since it's a rectangular shape, then y goes to from 0 to, let's say, b over 2, and x goes from 0 to b over 2, 1 over square root of x squared plus y squared plus b squared. So you first, you first need to take one of the integrals. So if you consider the y integral only, it is this kind of an integral, let's say, delta squared, where now delta squared is x squared plus d squared. Now, how do you take such an integral?
I tried to change the first zero.
Not the inverse, just make the change of variable y theta, delta, tangent theta. Now, the general trick, if you have, let's say, something squared plus your integration variable squared plus some constant squared, the trick is always to make y is equal to delta tangent of an angle. Y tangent, because if you put it over here, y squared plus delta squared becomes delta squared tangent squared theta plus 1. And 1 plus tangent squared theta. Well, if you don't remember, this is sine squared theta divided by cosine squared theta plus 1, which is delta squared divided by cosine squared theta. So if you put it under the square root, you get delta over cosine theta, so that becomes cosine theta over delta, which is a much easier integral to evaluate. Of course, there's also the problem of dy. What is dy? dy is delta over cosine squared theta. So you had, from this 1 over square root, you get cosine theta. From dy, you get 1 over cosine squared theta. So the result is the integral of 1 over cosine theta. So that is the integral you need to evaluate.
You mean another d theta there?
Yes. So you convert the integral to the integral of 1 over cosine theta. Do you know how to evaluate that? Well, what is the integral of d theta over cosine theta?
Hocam gelen sekant x artı tanjant x var direkt. Yani theta
Well, there are a couple of tricks you can do here. Well, the one I like is, well, I personally like, I find it easy to remember, is to write this as d phi over sine phi. Just make a change of variables. Phi is theta minus pi over 2, let's say. This is d phi over 2 sine phi over 2 cosine phi over 2. I want to use this trick. This is equal to cosine squared phi over 2 plus sine squared phi over 2 divided by twice sine phi over 2 cosine phi over 2 d phi, which is 1 over 2 cosine phi over 2 over sine phi over 2 plus sine phi over 2 divided by cosine phi over 2 d phi, which is 1 over 2. Remember, the cosine is nothing but the derivative of sine. So logarithm of sine phi over 2 multiplied by 2 minus the logarithm of cosine phi over 2 multiplied by 2 plus your integration constant. So you have the integral. Of course, then you have to express phi in terms of theta and then theta in terms of y, and you are done. Now, rather than just trying to remember what are the integrals of 1 over sine phi, I personally find it easier to remember the tricks that I use to evaluate it. So that when I need it, I can just reevaluate it. Okay, this was one of the, well, let's say, technically complex problems. The other one was the ellipsoid, where there was also some mathematics in the ellipsoid. Shall we also discuss how to solve the problem of the ellipsoid? Well, if you remember, the problem was we had this ellipsoid of revolution, so which was given by x squared over a squared plus y squared over b squared plus z squared over c squared. This is equal to 1. This is the equation defining the surface of the ellipsoid. Well, there are two things you could have done. You can still do. One is, okay, this looks quite similar to the sphere. If A and B and C, they were equal, then it just becomes a sphere. Now let's get rid of the A, B, and C. Let's define new coordinates. Let's say x is equal to A times u, y is equal to b times v, and z is equal to c times t, let's say. Then u squared plus v squared plus t squared is equal to 1. So in this u, v, t space, let's say, it is a sphere, not an ellipsoid. Of course, we have to convert our problem to the ellipsoid problem also, to these new variables. So that kind of can be tricky. But we are given the surface charge density at the point x, y, z. This had a given expression. You know the expression in your book, in your homework. Well, I can convert this to a volume charge density. You see, this, I can solve for, let's say, one of the variables. So it tells me that z squared is equal to c squared times 1 minus x squared over a squared minus y squared over b squared. Or my surface is defined as, I have two equations for z. Z is equal to plus or minus c 1 minus x squared over a squared minus y squared over b squared to the power 1/2. This is the equation for my surface. So this volume density would be sigma x, y, and z. Dirac delta Well, the surface density is at z is equal to c times that square root. Or it is also at minus c times that square root. This is my volume density. So the total charge would be the integral of rho over all space. Well, now I can make the change of variables. You see, these are my change of variables. So Q tot would be equal to rho of AU BV CT times ABC du dV dt. Now, if you write the expression for rho AU BV CT, this would be sigma AU BV CT, whatever the expression is, times the Dirac delta. Well, Z is now CT minus C 1 minus x squared minus y minus u squared minus v squared under the square root, plus the other Dirac delta would become CT plus C 1 minus x squared minus v squared minus u squared minus v squared. Well, these Dirac deltas just tell me that the integral over du dv dt, you see this Dirac deltas, Ct plus or minus c 1 minus u squared minus v squared square root, this is nothing but 1 over c Dirac delta t plus or minus 1 minus u squared minus v squared to the 1/2. But these Dirac deltas just tell me that I am integrating over the surface of the sphere in the UVT space. So I converted my problem of the ellipsoid of revolution to a problem of a sphere. And the surface integral of the sphere, you can just evaluate it. This is one way. Well, you see, dx is equal to a times du, and dy is equal to b times dv, dz is equal to c times dt. Since I'm not mixing the coordinates, I don't really worry about the Jacobian. But of course, if you could have done the same thing, obtained the same ABC factor by calculating the Jacobian. Now, this is one way, just using the things that you already know. Well, there's another method. Let's discuss that one also a bit. I mean, do you have any questions on this one? Well, the idea in this solution was basically to convert a problem that you don't know how to calculate to a problem that you can actually calculate. A sphere you can calculate, an ellipsoid you cannot calculate, but it's not so hard to transform an ellipsoid into a sphere. Let's do the other part, other alternative. Now, the total charge is nothing but sigma ds. So we have to evaluate this ds, this surface integral over the surface of the ellipsoid. Now, of course, sigma is expressed in terms of x, y, z. And so what is the surface element? ds in terms of x, y, and z. So that's kind of the hard part. How can we express ds? I mean, ds is not just dx or dx times dy in this case. Now, if you, how do we define that ds? Let's take our ellipsoid. We take some patch over here. This is the patch on the surface of the ellipsoid. So this is our ds vector. Now, if I take the, let's say, if I just look at it straight from the top, this is x, this is y, this is the z. Well, if you look at it straight from the top, the surface is just an ellipse. That ds surface is somewhere over here. And I want to choose this ds such that when I look at it from the top, I see a rectangle with sides dy and dx. So basically, this is my surface. On the xy plane, I choose a rectangle. When I kind of lift the rectangle on the surface, I will have some kind of an inclined surface. So the area of this patch is dx dy. That is nice. But the area of the surface of my ellipsoid is not equal to that area. It's different. So I have to kind of calculate this area first. And then I will be able to convert my integral into an integral over x and y. That's what I will be trying to do. How can we calculate this surface element over here? In fact, you already have the tools. Let's remember what the cross product is. This is the vector A, this is the vector B. A cross B. What is the magnitude? AB times sine theta. This is the magnitude of the cross product. So if this length is A, then this length over here is A times sine theta. So if you imagine a parallelogram, what is the area of this parallelogram? This side is B, the height is A sine theta. Area is nothing but the magnitude of A cross B. What is the direction? Well, inside, perpendicular to the area. Well, that is my area vector, actually. Either A cross B, or, well, we know that we can choose the area vector in both directions, either into the screen or out of the screen, or S is equal to B cross A. You can just choose whichever one you like. And in fact, let's imagine this area. Well, we said that if we choose a direction for our area, we also choose a direction for the boundary of the area. Do you remember that? In your first year? Basically, that's the cross product, is A cross B. So if you look at, for example, A cross B, you are basically rotating A towards B. Now, that is the direction of the boundary of this area. So if you define S to be A cross B, then the direction of the boundary is this one. You are rotating A to B. So that's, in fact, why we define that area. Why we define that sense of the loop. Now let's come back here. So we know how to define, how to calculate areas using vectors, including their direction. We can even define their direction. Now, what was our problem? We had the surface over here. We took some patch over here. We are trying to calculate this area. So what we need to do is we need to calculate a vector pointing along this side, another vector pointing along that side. If we take the cross product, that is our area vector. If we take the magnitude, we have the area of that patch. That is what we will do. Any questions? Now that vector, let's say V, we will have both of them. We have this patch. I mean, I'm first let's look at an arbitrary vector. This vector is nothing but the vector connecting these two very nearby points. So I take two nearby points at the corners of my rectangle and just write the vector connecting the two by subtracting their positions. Now these 2 points will differ in their x-coordinate by dx. Their y-coordinate will differ by dy. And their z-coordinate will differ by dz. So this is kind of great. So if we can identify dx, dy, dz, we know our vector along this side. And if we can identify that other vector along the other side, then we know both of our vectors. Now, remember we have this rectangle over here, dx, dy, on the xy plane. And each side of this rectangle on the xy plane will basically correspond to one side on our surface. So we have this dx, dy. Well, let me just make a change here. Let me call them, give these ones slightly different names. No, not really. I will give them dx, dy, because this dx, dy on the surface is actually the same dx and dy on the top. Because how do we evaluate the point on the surface? We pick up a point here, and we calculate the height at that point. We take the next point, we calculate the height. So if I change the x-coordinate of my point on the xy plane, the corresponding three-dimensional point, the x-coordinate will change by the same amount. It's just their heights will be different. So this dx, dy here on the xy plane is the same as dx, dy on the top. Now, as I move along this side, so what I do, how I project this rectangle to my surface, for every point on the xy plane, I calculate the corresponding point on my surface. So I move along this line, that will give me one side of the surface on my ellipsoid. But as I move along this line, I'm not changing y. Y doesn't change along this direction. So dy is 0 along this line. So that is one of my vectors. V1 is equal to dx in the x hat plus dz in the z hat. Let me call them dx1. No, that is dx. Let me call this dz1. Why I say dz1? Because when I'm evaluating this dz, I am assuming dy is equal to 0. So I should calculate the change in the height as I change the x-coordinate by this much, keeping the y-coordinate constant. Now, as I move along this line, then dx is not changing. So that gives me another side of the corner of my surface, V2. This is equal to dy y hat plus dz 2 z hat. This time dx is equal to 0. So now I have my vectors v1 and v2, which specifies both sides of my surface on the ellipsoid. In fact, any shape. Up to this point, I didn't use the fact that I'm working on an ellipsoid. This is quite general. So I have this arbitrary surface given by some function z is equal to some function of x and y. Then I take a patch on my surface. The two sides of this rectangular patch, I can just write like v1 and v2. And when I take their cross product, the s vector will be nothing but v1 cross v2. So the thing that is left is I have to calculate dz1 and dz2. To calculate dz1 and dz2, let's use the equation defining our surface. Remember, the definition of our surface was this one, x squared over a squared plus y squared over b squared plus z squared over c squared. This is equal to 1. This is the definition of my surface. So if I pick one point on my surface, the x, y, z coordinates will satisfy this one. I just move it slightly. The x coordinate will be different by dx. The y coordinate will differ by dy. The z coordinate will differ by dz. But this combination will not change. So that is the change in this one, if I consider two very nearby points, will be equal to the change in d1, the change in 1. 1 doesn't change on my surface. I'm considering 2 points on my surface. So this change should be 0 if I consider any 2 nearby points on my surface. Well, that gives me twice x over a squared dx plus twice y squared, twice y over b squared dy plus twice z over c squared dz should be equal to 0 for any 2 nearby points on my surface. Or let me also cancel the 2's. X dx over a squared plus y dy over b squared plus z dz over c squared. This should be equal to 0 for any 2 points on my surface. Now, how did we calculate V1? Well, I chose 2 nearby points on my surface. And those 2 points had the same y coordinate, so dy was 0. But their x coordinate differed by dx, and their z coordinates differed by dz1. So that dx, dz1, and dy is equal to 0 should also satisfy this equation, because this is valid for any 2 points. For V1, I just took some not so arbitrary 2 points. So x dx over a squared plus dy is 0, 0 plus z dz1 over c squared, this is equal to 0. So that tells me that dz1 is actually minus x dx over z and c squared over a squared. This is dz1. Well, I can do the same thing for V2. Again, remember what V2 is, just the vector connecting 2 nearby points, and those 2 nearby points had the same x coordinate. The change in the x coordinate between these 2 points was 0. So y dy over b squared plus z dz2 over c squared, this is equal to 0. Or dz2 is equal to minus y over z dy b squared over c squared over b squared. This is my dz2. So now I know what my v1 and v2 vectors are. This is equal to dx is a common factor. X hat minus x over z, c squared over a squared z hat. In the V2, dy is a common factor. Y hat minus y over z, c squared over b squared z hat. Now I can calculate their vector product. This is equal to dx dy times x hat minus x over z, c squared over a squared z hat, cross product with y hat minus y over z, c squared over b squared, again z hat. Well, we can just calculate that scalar vector product. Open up the parentheses. X hat cross y hat is z hat. Now, x hat cross z hat is minus y hat. There's another minus over there. So it will be plus y hat y over z c squared over b squared. Then z hat cross y hat. Z hat cross y hat is minus x hat. So again, plus x over z c squared over a squared x hat. And z squared cross z squared, 0. So this is my vector product. This is my ds vector, if you would need it. Well, in this problem, we don't need the direction of the ds vector. We need the magnitude of this ds vector. So ds magnitude is dx dy, 1 plus y squared over z squared c squared over b squared plus x squared over z squared. So this is c to the 4, b to the 4, c to the 4 over a to the 4, everything under the square root. This is our ds area. Then, of course, you have the integrals, not so trivial integrals, but nevertheless, if you look, I mean, you can just take the z as z. You have to replace z by its expression in terms of x and y. You see z squared was c squared times 1 minus x squared over a squared minus y squared over b squared. You have to put this over here, take the x and y integrals. Now, it will be technically complicated, but conceptually, these are all the new concepts you need. Now, of course, in identifying the boundaries of x and y integrals, you have to be careful also. You see, on the xy plane, your integration region is this one. This is a, this is b. X squared over a squared plus y squared over b squared. This is equal to 1. This is your integration region. By the way, now you can go to some kind of angular coordinates. Instead of x and y, let's say you can define x is equal to a times r times cosine theta, and y is equal to b times r times sine theta. Or let's say this is your domain less than or equal to 1. Then the x dy region will be just the dr d theta, but you will have the Jacobian of transformation. But the nice thing is r will go from 0 to 1, theta will go from 0 to 2 pi. They will be independent of each other. If you stick with your x and y integration, you can say that x will go from minus a to a, and y will go from minus a times square root of 1 minus y squared over b squared, x squared over b squared, to plus a times square root of 1 minus x squared over b squared. With these new variables, your integral will be much simpler. Now you see ds looks quite complicated in terms of x and y. If you just define these variables, it will also simplify significantly. So the remaining integral will be much easier to evaluate. So here, let's say, okay, there are these technical things about how to evaluate this integral. The new concept is how do you define the areas? And we said that, okay, vector product is our friend in defining areas.
Anlamadım hocam, zaten alanları tanımlamadık mı A equals diye?
What are A and B in our special case of an ellipsoid?
Şu V1, V2'de.
Yes, that's what we did. We found what V1 and V2 are. Once we could determine what V1 and V2 are, then our area element is nothing but V1 cross V2 or V2 cross V1. So remember, you have two choices for the choice of the area vector. Do you define it as V1 cross V2 or V2 cross V1? Up to you. Anyway, in this problem, it doesn't really matter because what we are interested in is not the direction of the area vector, but its magnitude, which is this one.
Çok da bir şey değişmedi hocam.
Hmm?
Ben bunu yazsam integralini alalım.
Well, let's see. This is our ds. Let's first calculate what z is. Z squared is c squared times 1 minus x squared over a squared minus y squared over b squared. So c squared times 1 minus x squared over a squared is, well, x over a is r cosine theta, r squared cosine squared theta minus r squared sine squared theta to the power 1/2. So this is c squared times 1 minus r squared to the power 1/2. So z squared looks quite simpler. And remember, theta integral and radial integral now have independent limits. So you just need to take, oh, this is z squared. So let's write the ds. I will keep the dx dy. So you have to convert it into r and theta, dr and d theta. With the Jacobian, you have to calculate the Jacobian of this transformation. Dx dy times 1 plus, well, you see y squared over z, y squared is b squared r squared sine squared theta divided by c squared 1 minus r squared. Now, in z squared, I don't have that square root. This is the y squared over z squared times I have c to the 4 divided by b to the 4 plus I have b squared r squared cosine squared theta divided by c squared 1 minus r squared times c to the 4 divided by, no, this is a squared, a to the 4 to the power 1/2. This is our ds. So do we have some simplifications? Well, here we have c squared, here we have b squared, c squared, a squared. So ds is equal to dx dy, 1 plus r squared over 1 minus r squared. This is common in both terms. Then I have sine squared theta c squared over b squared plus cosine squared theta c squared over a squared to the power 1/2. Well, somewhat simpler, not completely maybe. Just try to plug in dx dy and see if there are simplifications. Plug in the sigma. We haven't yet written down sigma here. We have to multiply this by sigma. Now, if you put in the sigma also, you will see that it turns out to be quite a simple integral. Just don't be afraid by the first sight of it. It will simplify. This horrible looking factor will cancel with sigma. What remains will be easy. Give it a try. Other questions? Now let's leave this aside. It was kind of a good morning example.
Yesterday, we showed that the first question of the homework was relatively easy by if we do it by viewing the square.
Okay, the first question of the homework is supposed to be, we have these 2 point charges.
But if we try to solve that, if from the potential of a dipole, it becomes somewhat
Well, you see, you cannot use the potential of a dipole here. It is a dipole, but you see the expression we obtain, this was equal to p dot r hat divided by r squared 1 over 4 pi epsilon 0, if I'm not missing any factors. This is valid if r is much, much larger than d. That expression is valid only in that case. But you see, the spheres we are trying to find look like this one. So we want to know the potential even between these 2 charges in this region where this is not satisfied. Since this is not satisfied, you cannot use this one.
this superposition of the potentials didn't work. And it is like
Let's see, what will be the potential at the point r? It will be 1 over 4 pi epsilon 0 q over r minus r plus 1 over 4 pi epsilon 0 q over r minus r minus, which is 1 over 4 pi epsilon 0 q 1 over r minus r plus minus 1 over r minus r minus. So you have to find points for which 1 over r minus r plus minus 1 over r minus r minus, this should be equal to constant, not 0, some constant. So what is the shape defined by this equation? That is what you need to identify. Now let's see. let's just choose some points. Let's say that r plus is at 0. I can choose my coordinate axis any way I like. And r minus is equal to d in the x direction. Let's just call it. This is x, this is y. And I know that I can just rotate my system around this axis. So if I can identify one point on the xy plane, if I just rotate it around, all those points satisfy the same property. So I don't really need to look for x, y, z coordinates, but it's enough for me to look at the x and the y coordinates. Let me not complicate with the z. So r minus r plus is equal to the magnitude of r, which is x squared plus y squared. R minus, this is equal to x minus d in the x hat plus y in the y hat. This is x minus d squared plus y squared. So the equation we have is 1 over square root of x squared plus y squared minus 1 over square root of x minus d squared plus y squared. This should be equal to some constant. So what is the shape? My claim is that it will be a sphere in 3 dimensions when I be rotated. On the xy plane, it will be just a circle. That is my claim. So what is the equation of a circle?
X kadar eşittir rakam.
No?
X minus d squared plus y minus b squared plus r squared is a circle something.
Yeah. Or x squared, let's say minus 2ax plus y squared minus 2bx by should be equal to some c squared. Can you convert this equation into this equation? So that's the question. If you convert this into this equation or an equation that looks like this one, then you know that it's a circle with center at A and B. And since it looks like a circle on the xy plane, when we rotate it, it just becomes a sphere. Of course, this A and B will depend on what constant we have, and that constant determines the potential of our equipotential surface. So as you change the potential of your equipotential surface, its center will change, C will be related to the radius, its radius will change. It will get bigger and bigger.
Yani hocam bu constant değişince equipotential da mı değişiyor?
Well, you see, what is that constant? Our potential is 1 over 4 pi epsilon 0 q times, well, let me give that a name, C1 times C1, because our potential is 1 over 4 pi epsilon 0 q times this difference. If I call that constant C1, my potential is also changes. Because this is the potential of my equipotential surface. Now, I didn't say to use the method of images to solve this problem. What I said is, once you solve this problem, you can use the method of images to solve the problem of two conducting spheres, two charged conducting spheres. Because then we will know that these two spheres, we can replace it by point charges. But you see, yesterday, what I said was, once you solve this problem, you will know that if you have these 2 point charges, the equipotential surfaces are just spheres. The method of images basically tells you that if you change an equipotential surface by a conductor, nothing changes. So that is an idea of the method of images. So instead of, let's say, here we have these 2 charges. So if you find that this is an equipotential surface, replace this equipotential surface by a conducting sphere with a total charge plus Q, and the electric field in this region doesn't change. So you already know the solution of the electric field in this region, let's say, of the problem of a point charge and the conducting sphere. If this is also another equipotential surface, just replace this one by a conducting sphere of charge plus Q, replace this one by a conducting sphere of charge minus Q, and if you need to find the electric field everywhere outside, you are done. Because outside, it just looks as if you have 2 point charges. Inside, they will look different. Inside these conducting spheres, the electric field will be 0, but outside, they will be the same.
Yani ilk önce bu equipotential'ın küresel olduğunu ispatladı.
Yes. Well, in fact, whatever the shape, being sphere is not really important. The idea is you can replace any equipotential surface if it is closed. Well, the equipotential surfaces are usually closed. If you replace any of the equipotential surfaces by a conductor that has the same charge as the charge inside your equipotential surface, nothing changes. That's the basic idea. Even if the equipotential surface has a weird shape, just put a conductor with that weird shape. For example, in your next homework, you will have 2 cylinders, not concentric, side by side. And then you will be asked to find the potential everywhere. Now, you will be guided. There will be detailed step-by-step instructions on how to find the potential. But the idea will be basically the same. If you just first study the problem of 2 infinite straight wires carrying uniform charge density, then show that the equipotential surfaces are cylinders, then you can just replace any one of those cylinders, any one of those equipotential surfaces by a conducting cylinder. Or you can go the other way around. If you have these cylinders, you can just convert them into a problem of 2 infinitely straight uniformly charged wires. And we already know the potential and the electric field of a straight uniformly charged wire.
Ve bu method of images'i her zaman kullanabilir miyiz?
Well, let's see. What were the cases that we used the method of images? Planes. Either infinite straight plane or planes at particular angles. We studied the example of spheres. And now we are saying that even if you have 2 spheres, not a sphere and a point charge, even for 2 spheres you can use it. For cylinders you can use it. That's kind of it. Because still we need to have the shapes of your conductors should be sufficiently symmetric. Otherwise, you will not be able to find a finite number of images.
Bu hani Gauss surface seçiyordu diyorum. Bununla bağlantısı olabilir mi? Method of image.
Well, you see, here the problems we are studying here are less symmetric than the ones that we use to Gauss law. For example, for the Gauss law, we could only study an isolated charge sphere. Now, if you have a sphere plus a point charge, Gauss law doesn't really help. But in method of images, you can still use it. With respect to the symmetries, you can say that the method of images is less demanding than the Gauss law. But nevertheless, you still need to have sufficient symmetry. Okay, let's give a 10-minute break. And after the break, you can come up with your questions.